In this video, we are going to look into chemical consequences of electron delocalization. A molecule with delocalized electrons is more stable compared to a hypothetical molecule that would not have delocalized electrons. And we can actually calculate the exact amount of energy that is due to electron delocalization. We call that resonance energy. The process of calculation of that energy is shown here on example of benzene. So if we want to calculate by how much benzene is stabilized due to electron delocalization, we start with cyclohexene, compound that has only one double bond in a six-membered ring. Upon hydrogenation of cyclohexene to cyclohexane, 28.6 kilocalories per mole are released. Obviously, that's exothermic process. Now, in case of hydrogenation of benzene to the same compound, cyclohexane, under the same conditions, 49.8 kilocalories per mole are released. And so from these two values, we can calculate the amount of stabilization due to electron delocalization. Here is the calculation. So if pi electrons in benzene were not delocalized, then there would have been 3 individual localized double bonds. And each double bond would release amount of energy that we have determined by hydrogenating cyclohexene. So 3 times 28.6 kilocalories per mole, or total of 85.8. But molecule of benzene releases only 49.8. Difference is 36 kilocalories per mole. This is by how much benzene is stabilized due to electron delocalization. That's very large amount, and that's very high degree of stabilization. That's why benzene is an aromatic compound. So aromatic compounds have especially high degree of stabilization due to electron delocalization. And this is shown here in a graph. So hypothetical 135 cyclohexatriene would have rather high energy of, with very high amount of energy released upon hydrogenation, and that's shown here. 135 cyclohexatriene is shown with exaggerated bond lengths, double bond much shorter than single, to emphasize that this hypothetical molecule with localized electrons. And then benzene releases only 49.8. So the difference is 36.0 delocalization energy or resonance energy. And we can show that this process is correct by carrying out control experiment on 1,4-cyclohexadiene. Hydrogenation of 1,4-cyclohexadiene releases 57.4 kilocalories per mole. If our reasoning is correct, then the amount of energy should be twice the amount of energy released upon hydrogenation of cyclohexene. And so when we calculate 2 times 28.6 is 57.2. That's the expected hydrogenation energy of 1,4-cyclohexadiene, and the actual is 57.4, slightly higher, but within experimental error. So this shows that our reasoning is correct, that if one double bond in six-membered ring releases a certain amount of energy, 2 double bonds that are not delocalized should release twice as much, and then we can conclude that 3 should release 3 times as much. Now we are going to examine stability of allylic and benzylic cations. First, some definitions. Allyl cation is specific cation that has formula of C3H5+, of course, for cation. An allylic cation has substituent somewhere on the allyl carbons, 103 allyl carbons. And conversely, benzyl cation is a specific cation with a formula of C7H7+, and benzylic cation has substituent on benzylic carbon. That means that allylic cation could be primary, secondary, or tertiary, depending on degree of substitution, and the same for benzylic cation. Benzylic cation could also be primary, secondary, or tertiary. Both of them are stabilized by resonance, and we have seen that before, and we have seen their resonance structures before. Here, just to remind you, are resonance structures of benzyl cation. So both of these species are stabilized quite a bit through electron delocalization or resonance. And now we can include these resonance stabilized carbocations in the order of stability of carbocations. Primary benzylic and allylic cations are slightly more stable than secondary carbocation and less stable than tertiary. So that would be the order of stability. Benzylic with a little bit greater degree of electron delocalization, 5 resonance structures versus 2, is more stable than allylic. So this would be the order of stability. Tertiary is still the most stable, then primary benzylic, primary allylic, secondary, primary cation, then we can include vinylic. Vinylic is less stable than primary, but more stable than methyl. Make sure to distinguish between vinylic with positive charge on sp2 carbon and allylic with positive charge next to sp2 carbon. Obviously, great difference in stabilities. Also, keep in mind that only primary benzylic and allylic cations are less stable than tertiary. Secondary and tertiary allylic and benzylic carbocations are more stable than ordinary tertiary carbocation. Nomenclature of corresponding radicals, allyl radicals, allylic radicals, benzene and benzylic radicals, corresponds to that of cations we just covered. So allyl radical is specific radical with formula of C3H5. Allylic radical has substituent on one of those carbons. Benzyl radical, formula C7H7. Benzylic radical has one or more substituents. So allylic and benzylic radicals could be primary, secondary, or tertiary. And they are also stabilized through electron delocalization. In fact, degree of stabilization through electron delocalization is even greater than that of the corresponding carbocations. So when we consider order of stabilities, even primary benzylic and allylic radicals are more stable than a tertiary radical. So order of stability would be benzylic radical, more stable than allyl, then tertiary radical, secondary, primary, vinylic, and finally methyl. So now there is a difference in the order of stability of carbocations and radicals. In the examples that we have encountered up to now, carbocations and free radicals exhibited the same order of stabilities. But now, as you can see, there is a difference. In that, primary benzylic and allylic radicals are more stable than tertiary radical, while primary benzylic and allylic carbocations are less stable than tertiary carbocation. Electron delocalization affects reactivity and reaction outcome of molecules with delocalized electrons. For example, when we consider regioselectivity of radical substitution, this is something we have seen already before. Free radical substitution in benzylic and allylic positions is favored, and that's because intermediate free radicals are extremely stable. And we have just seen that the reason behind their high stability is in electron delocalization. So those are usually the only radicals that form in the course of reaction, and reaction is highly regioselective. Also, in case of an addition to an alkene, regioselectivity is affected by stability of the intermediate carbocation. So here we have an alkene where double bond is conjugated to the benzene ring. So addition proceeds in such a way that benzylic carbocation is generated, and reaction is extremely regioselective so that only one product is obtained. And again, that's the product that results from formation of the intermediate benzylic carbocation. Electron delocalization also affects the outcome of rearrangement of carbocations. So in this example of addition of hydrogen bromide to alkene shown here, first protonation results in formation of tertiary carbocation. Now, tertiary carbocation will not rearrange into another tertiary carbocation, as there is no gain in energy in the course of such process. Simply, two tertiary carbocations would be expected to have about same stability. So, tertiary carbocation shown at the bottom right would not be a result of the rearrangement. Instead, tertiary carbocation, that is result of protonation, rearranges into secondary benzylic carbocation. Secondary benzylic carbocation is more stable than a tertiary carbocation. And then it is this secondary benzylic carbocation that reacts with the nucleophile, accepts electron pair from the nucleophile to form carbon-bromine bond, and gives the final product. In an electrophilic addition to an alkene, substituents play a considerable role. They affect reactivity of the alkene and also they affect reaction outcome. Substituent may exert electronic or steric effect or both. In this case, we'll only focus on electronic effects. First, we are going to examine inductive effect. So, in the first equation, there is, in general terms, shown electrophilic addition to an alkene, and as a specific example, there is a bromination reaction in the second equation. An alkene, in this case, is a nucleophile, and it donates its electron pair to bromine. As a nucleophile, it will be more reactive if substituents are electron donors. So inductive effect is effect that spreads through sigma bonds. So substituents that are capable of donation of electron density through sigma bonds will increase reactivity of an alkene. And alkyl substituents or hydrocarbon substituents in general are such substituents, which means that with increasing number of alkyl groups on double bond, reactivity of that double bond increases. So this is the reactivity of substitute alkenes towards electrophilic addition. Tetrasubstitute is the most reactive, then trisubstitute, disubstitute, and finally monosubstitute. The least reactive is a molecule of ethene, which has no substituents. Besides the inductive effect, the other electronic effect is resonance effect that we have covered in this video. As a general rule, resonance effect is stronger than the inductive effect. And of course, it has effect or impact on reactivity of alkenes. Here we have 4 alkenes arranged in the decreasing order of reactivity. So first alkene has methoxy substituent, so oxygen as atom directly bonded to double bond, and oxygen exhibits positive resonance effect and negative inductive effect. As resonance effect is stronger than inductive effect, next effect is electron donation, and that means that reactivity of alkene is increased. In fact, it's increased by quite a bit. Phenyl group also exhibits positive resonance effect, electron donation through resonance effect through pi bonds, but not as strong as oxygen. So for that reason, magnitude of effect is weaker or lower, so reactivity of such alkene is a bit lower. Halogens are an exception. Halogen atoms exhibit positive resonance effect, but also negative inductive effect. And in halogens, inductive effect is stronger than resonance effect. So they exhibit net electron withdrawal. So the alkene shown here with halogen as substituent, halogen in allylic position, is less reactive than previous alkene. Previous alkene is actually called styrene. And that's because the overall effect is electron withdrawal. And finally, an alkene vinyl chloride is even less reactive because chlorine substituent is even closer to the double bond, to the reactive site, to the pi system. Resonance effect or electron delocalization through pi bonds also affects regioselectivity, and we can see that on example of methyl vinyl ether. As we have just seen, methyl vinyl ether is very reactive, so due to resonance effect it has high reactivity, but also in reaction with an electrophile such as hydrogen bromide, regioselectivity is affected. So protonation occurs on carbon away from oxygen, so that resulting carbocation is stabilized through resonance with oxygen, or formation of oxonium ion. And then carbon that is bonded to oxygen forms bond with bromine, reacts with nucleophile to forms bond with bromine. This reaction is highly regioselective and only one product is obtained. Finally, here is a list of common substituents and their resonance effects. So positive resonance effect means electron donation through resonance effect or through pi bonds, and substituents that exhibit positive resonance effect are those substituents that have free electron pairs. Those with negative charge exhibit stronger effect, and those that are neutral weaker. Substituents are listed in the decreasing order of magnitude of resonance effect. So alkoxide anion, oxygen minus, exhibits the strongest effect, while halogen the weakest. To the right, in the right column, are substituents with negative resonance effect. They exhibit electron withdrawal through pi bonds. And again, they are listed in the order of decreasing effect. So those are substituents that either have positive charge or partial positive charge, and in general are electron deficient substituents. And the greater degree of electron deficiency, the stronger the effect. Finally, at the bottom, in a green rectangle or green field, substituents that are shown are substituents that could exhibit either positive or negative resonance effect. They are capable both of electron donation and electron withdrawal through pi bonds. Sometimes we say that they serve as electron buffers. So they may, whatever is needed, they may donate or withdraw electrons, whatever substrate needs to undergo a reaction. This completes our study of chemical consequences of electron delocalization, and next we are going to look into dienes and polyenes.